Welcome to today's Explainer. We're diving straight into some foundational math concepts, specifically breaking down the real rules behind numbers. You know, if you've ever stared at fractions and thought, okay, but what's the actual system here? Well, you're absolutely in the right place. We're going to make the whole shebang super clear, highly accessible, and practically impossible to forget. So let's jump right in. Here is our roadmap for today. We've got a quick Chapter 1 overview, then we'll define exactly what rational numbers are before breaking them down into positive and negative categories. Simple as that. Section 1. Chapter 1 Overview. The road ahead. Zooming out for just a second to look at the bigger picture. After today's introduction to rational numbers, we're going to be tackling the specific properties of adding, subtracting, multiplying, and dividing them. It's essentially a complete system of math operations. But today is all about laying that unbreakable foundation, so when we get to the heavy lifting later, it'll be an absolute breeze. Moving right along to Section 2. What are rational numbers? The core formula. Let's get to the main event and define what a rational number actually is. Think of it like a secret code or a highly specific format. It's written simply as a fraction, a divided by b. The catch? Both the top and the bottom absolutely must be integers. So you've got your top number, the numerator, which we'll call a, and your bottom number, the denominator, called b. As long as both of those pieces of the puzzle are integers, boom, you've got yourself a rational number. But hold on, because we need to slow down for the single most critical rule of the game. Your denominator, that b on the bottom, can never, ever be 0. Now, you can totally have 0 as your numerator, your a. That's perfectly fine. But the literal second your denominator becomes 0, the whole mathematical universe basically shatters. The structural integrity just falls apart, and it ceases to be a rational number at all. It is the ultimate, non-negotiable rule of the road. To put this into perspective, let's fire through a few valid everyday examples. 5 over 8? Rational. -3 over 11? Also rational. 7 over -15 and -6 over 11. All perfectly valid. Why? Because they strictly follow our format of an integer over an integer, and, crucially, that bottom number entirely avoids 0. You could literally invent endless examples yourself, like 8 over 9 or, I don't know, -11 over 15, just as long as you respect that golden rule. Section 3. Positive rational numbers. The sign detective. Now that we've got the basic format locked down, let's play detective and figure out how to actually classify these things, starting with positive rational numbers. The absolutely crucial point here is that for a fraction to be strictly positive, the top and bottom must match in their signs. Take 5 over 7. Both are positive integers, making the entire rational number undeniably positive. Pretty straightforward, right? But wait, what about the second half of that definition? Let's test this out with a little mini mystery. Think about the fraction -2 over -3. At first glance, with those glaring minus signs staring right back at you, does that feel positive or negative? I mean, your initial instinct probably screams negative purely because of what your eyes are seeing. But here is the real plot twist. Those negative signs actually cancel each other out completely, making it a positive in disguise. The minus on the top 2 and the minus on the bottom 3 mathematically eliminate one another. Poof, gone, leaving us with a straightforward 2 over 3. And that is exactly why our definition states that if both the numerator and the denominator are negative, the overall rational number is firmly and undeniably classified as positive. Which brings us to Section 4, negative rational numbers. Opposites attract. All right, let's see how this all builds together with our final classification. With negative rational numbers, the rulebook basically flips. A rational number is classified as negative if, and only if, the top and bottom have completely opposite signs. If your numerator is positive, your denominator has got to be negative. If your numerator is negative, your denominator must be positive. It's a hard and fast requirement for this specific category. You can see this pattern play out perfectly in a few examples. Take -4 over 9, numerator is negative, so the denominator is positive. Or flip it. 5 over -12, where the top is positive and the bottom is negative. We've also got -8 over 9 and -24 over 90. In every single one of these cases, the top integer and the bottom integer sit strictly on opposite sides of 0. It's almost like they're magnetically repelling each other. So if we distill all of this down to an ultimate, at-a-glance takeaway, it's this. Matching signs equal positive, while opposite signs equal negative. Positive rationals require harmony. The signs have to match. Negative rationals demand a clash. The signs have to be opposites. It really is that straightforward once you know what to look for.
As we wrap up today's explainer, I want to leave you with something to chew on. Think about that golden rule exception we talked about earlier. We know 0/5 is perfectly valid, but 5/0 literally breaks the universe. So what actually happens when we start throwing these numbers together in equations? How do these positive and negative properties interact when we start adding them up? Keep that question right in the back of your mind, because it's exactly the puzzle we'll be piecing together next time when we dive into the properties of addition. Thanks for hanging out and learning with me today.